Hey everybody, just wanted to go over a quick tree diagram example here for you so we can kind of talk about what these tree diagrams actually do and how we can kind of make it work for us. So this question here is talking about a computer-based test for ovarian cancer, and it examines a blood sample for the presence of certain patterns of proteins. Ovarian cancer, though dangerous, is very rare, afflicting only 1 of every 5,000 women. The test is highly sensitive, able to correctly detect the presence of ovarian cancer in 99.97% of women who have the disease. However, it is unlikely to be used as a screening test in the general population because the test gives false positives 5% of the time. Why are false positives such a big problem? Draw a tree diagram to determine the probability. So what we're going to do is we're going to start off, and a tree diagram kind of goes through the possible branches. So the first thing is we know that cancer and then no cancer are two options. All right. This is 1 out of 5,000, which if I wanted to could be 0.0002. And then this is obviously 0.9998. So that's the chances you have no cancer. This is the chances that you do have cancer. Now, the next step comes in is when we know that if somebody has cancer, you either get a positive test or a negative test. Now, the test is extremely accurate if you have cancer. In fact, it's 99.97% accurate. So we're going to change that to a probability. We're going to say 0.9997, which means that we only get a false negative 0.0003 of the time. For no cancer, though, we get this false positive that occurs 5% of the time. So that's 0.05 here. That makes this 0.95 of the time we'll get a negative. Now, essentially, we're talking about probability of getting cancer and getting a positive test, probability of getting cancer and getting a negative test, probability of having no cancer and getting a positive test, probability of no cancer and getting a negative test. And so because these probabilities are the way they are, we multiply them together. And so here, for this possible outcome, we do 0.0002 times 0.9997. And that turns out to be a really small number, 0.000199994. And so that's the probability that you have cancer and have a positive test. Now, for a negative test, when you have cancer, it's 0.002 times 0.0003, which is an even smaller number of 0.00000006, I believe. And then we do the same thing down here. We multiply this 0.9998 times 0.05. And this is the probability that we have no cancer and a positive test, which turns out to be 0.04999. And then we do the same thing for no cancer and negative test. So that's 0.998 times 0.95, which is 0.94981. So essentially what we have is we have 4 disjoint outcomes: cancer positive test, cancer negative test, no cancer positive test, no cancer negative test. And the problem that we're coming up with using this test, going back to the original question, is we want to know, like, what happens or what's the probability of having cancer given that you have a positive test. And so that's the problem that we want to look at. Well, our formula says probability of cancer and positive test, over probability of positive test. Well, cancer and positive test is right here. So that's 0.000199994 over probability of positive test. Well, positive test is that one there and this one here. So I got to add those together. 0.000199994 plus 0.04999. That gives me 0.000199994 over 0.0501894. End result 0.00398. So why are false positives such a big problem? Well, the answer is this is the probability that you have cancer if you have a positive test. That's 0.398%, which is a very, very small chance. And so if you think about it, yes, that's great that you have a positive test. However, the chances that you have cancer given your positive test in this situation is very, very small. And so why scare everybody, like 99.602% of the population, if they're just going to get a positive test? So this tree diagram kind of helps us out. We're going to do another video where we do a two-way table and a tree diagram so you can kind of compare and contrast and see which one you like the best.